I used to wonder what exactly is a null space. It was confusing, and even when solving problems, I found myself just solving the steps without really understanding the concept. I was basically just memorizing the process. But then I started digging deeper, visualizing what the null space really represents. And that's when everything started to click. Welcome back, everyone. So far, we have explored one of the four fundamental spaces, the column space. In today's video, we are going to dive deeper into the null space and break it down visually for both 3 by 3 and 2 by 2 matrices. The visualization you are seeing right now on your screen here, this blue YZ plane is nothing but the column space of a matrix, and the vectors green vector, blue vector, and purple vector lying in the column space is nothing but column vectors of that column space. Whereas the white line passing through origin and passing through that red vector is nothing but the null space of the same matrix whose column space is this YZ plane. So here is the column space and null space for the same matrix in one picture. So let's get started. Exams. So first of all, null space is also called as kernel. All right, the kernel of the matrix is same as null space. So the definition is like the set of vectors that lands on the null vector, that is the zero vector, after applying the linear transformation, that is also a matrix, is the null space of that linear transform or matrix. Okay, so if we write this down mathematically, then let us suppose we have a m cross n matrix. All right, so a m cross n matrix with columns a1 up to an. So because this is an m cross n matrix, so there will be n columns, right? So these n columns are a1 up to an, and all the n columns ai will belong to rm, right? Because it's an m cross n matrix, so there are n columns. Each column vector belongs to rm. All right. So the null space also represented as NA. So null space of A is nothing but all the vector x which belongs to Rm, such that when you transform that vector x using the matrix A, what we get is the zero vector. That is, if we simply say in simple terms, we can say that the matrix A is mapping the vector x to 0, right? So we have seen what a matrix do. It is nothing but a linear transformation, right? A matrix is nothing but a linear transformation. So for example, you have x before the linear transformation, then a of x, it got transformed, right? This is a of x, it got transformed by the matrix A. So if x got transformed to from this vector to this vector, then it could be possible that there could be some another x. There could be some another x, maybe let us suppose somewhere here. There could be some another x somewhere here, which got transformed from x to zero vector. That is this zero vector. So after applying the vector x, after applying the matrix A to the vector x, that is transforming the vector x using A or the matrix vector product, we got the zero vector. So this vector x got knocked down to zero vector or origin in this case, right? So it could be possible because matrix is doing transformation, it is moving vectors from one place to another place, right? So it could be possible that some of the vectors are knocked down to zero vector. So such vectors, the set of all those vectors x, which after applying the matrix A got transformed to the zero vector, or also known as the null vector, is nothing but null space, the set of all such vectors. All right, so we can simply say, for example, we have this ax equals to v. This is a general representation, right? So what we are saying that the vector x, initially we have this vector x, okay, and then after applying the matrix A or the linear transformation A, we got the vector v, right? So if this vector v is nothing but the zero vector, right, that is a null vector, then the solution, that is set of all x vector, is null space, okay, or kernel of matrix A, right? So we can simply write this as Ax equal to all zeros. So this is basically, if you are asking a question, if you are asking a question, that this is basically saying that if you are asking a question, which all x when transformed by the matrix A lands on zero vector, that is origin in case of R2. See, zero vector is an abstract concept. It doesn't always mean origin. Here we are talking about the XY R2 plane, right? But in the previous lecture, we have seen that vector spaces could be of matrix as well, which we call as matrix space. It could be a function as well, which we call the function space, right? So in the case of matrix, is the 2 cross 2 vector space of 2 cross 2 matrices. What is the zero vector? The zero vector is nothing but a 2 by 2 matrix of all zeros, right? So this is the zero vector of 2 cross 2 matrix space. All right, this is the zero vector of 2 cross 2 matrix space. This is the zero vector. This is the zero vector of R2 XY plane. All right. Similarly, we could have zero vector for function. Basically, it is nothing but just zero. I mean, because you have no components at all. So that is the zero vector for the function space. So you can have zero vector. It's an abstract concept. Okay. So when I say this, this is like if you are asking that which all x when transformed by A lands on zero vector, that is zero, that is origin in case of R2. So we are asking this question, that what are the set of those x? All right, it could be either only one possible value, that is the origin, that is before that is origin itself is mapping to origin. There is no such vector existing which got transformed to zero vector. It could be possible. Or another case is that an entire line of vectors got smacked down to the origin or the zero vector. That could be possible. We will see that is in different thing, but we will see that. All right. So now, I will show you some visualization. All right. I will show you a visualization of what is uh, null space. Okay. So let us suppose we take this matrix. Let us suppose we take this matrix uh, 3 0 and 2 0. Okay, 3020. So if you see, both these two columns are linearly dependent, right? They both lie on the x-axis, so these are linearly dependent. So if you have seen, if you have studied the last lecture, then you know that the column space is nothing but the x-axis. The dimension of column space is just one, because the column space is x-axis, because both the column vectors are linearly dependent and they are lying on the x-axis. Okay, now we will see the null space. So this is the visualization tool. So this is the matrix 3020. So it's because it's nearly zero, because this tool is like we need to place these dots, so it's difficult to place them precisely. But you can assume it as a matrix 30 and 20. All right. So first of all, we can also directly calculate what is the what is the null space of a matrix. So there is a tool. I will share it in the link. All right. So this tool, in this tool, you can simply enter the matrix. This is 3020 2 by 2 matrix, and then you can calculate. It will give you the null space. So in our case, for this matrix 3020, the null space is nothing but this minus 0.67 and 1. Basically, null space is will be the span of this vector. So because it's a single vector, the span of this vector is nothing but a line, right? So this is the null space, minus 2 by 3 1 times t, where you can change t, I mean 1 2 3 0.1 anything. So this is that vector, right? 0.67 and 1. So this vector is lying in the null space. Okay. So in fact, the entire line which passes through this vector, the entire line passing through this vector is lying in the null space. So we will see that when I play the animation, you will see that this green vector, that is the I hat, will move toward this green dot, because this is 3 0, right? So we have seen that what this means. This basically means where I had landed, right? So where I had landed, and this basically means where J had landed. All right. So you will see that this green arrow will slowly move to this green dot. Okay, this green arrow will slowly move to this green dot, and this red arrow will slowly move to this red dot. Okay. Then you will see that this vector and the entire line passing through this vector will be smack down to origin, because this vector is lying in the null space of this matrix, and all the vectors passing through this vector, or all the vectors lying in that line will be smack down to this to the origin. So, and this x-axis, right? The green vector, this x-axis is nothing but the column space. So we can see that this x-axis is the column space, and the line passing through this yellow vector is the null space. So I will play the animation now. So now you will see this vector, this line passing through this green vector is the column space, and you can see this line passing through this uh, yellow vector is the null space. So just focus on this line, focus on this line and this yellow vector. You will see that this will slowly all the vectors on this line will slowly go to origin. You will see this yellow vector at the end of the animation will boil down to origin. So I will just move. See, I'm moving. So you see, if you fast forward this section of video, you will see that this space is kind of squashing, like it is compressing. You will see that the space in this direction along this line will compressing, and it is compressing to origin, when boiling down to origin. See, now you will see these vectors, all these vectors slowly getting moving towards origin. See. Now you will see this entire line is moving toward origin. So all the vectors lying on this line are moving toward origin, and slowly everything on that line, see, at the end everything in that line, if you see, this is that line, this one, right? This is the line at the end. See this line, this one. You see everything has boiled down to zero. So this line of vectors, this line of vectors is nothing but the null space, and the set of all these vectors is the null space. Okay, so basically this is null space, so it's pretty simple, right? It's very easy. Now we will simply check, is null space even a subspace or not. So if I ask all of you the question, you can pause the video and think about that. Is null space of A is a subspace? This is the question. So you can pause and think about that. It's a good exercise. So first of all, I already told you that the first thing we check is, does zero vector belong to null space or not? So yeah, zero vector belong to the null space of A. Why? Because as A times zero vector is always zero, right? So you take any matrix, doesn't depend. Take any matrix. If you multiply any matrix with a zero vector, 0 0, you always get the zero vector, right? So the zero vector always belong to the null space. Now the second thing, let us suppose if A times X belong to the null space. Let us suppose we are saying that X, the vector X, when transformed by the matrix A, knocked down to the zero vector. That is, it moved to zero vector. It transformed to zero vector. So we need to check if this is true for c times x also, that is scaled version of x, we need to check that. So then is a does the matrix A also move c times x to origin or not? Let's see. In the previous lectures, we have seen that the property of matrix vector product, that c can be taken out, right? C times c into a times x, and we have already seen that x is in the null space. If x is in the null space, then a times x is 0. So this becomes this one, and c times 0 vector is always 0 vector. This is also the property of zero vector. We have seen that. So yeah, that this is also true. And the third one is, let us suppose if a the vector x, let us suppose vector x1. Let us suppose vector x1 belong to the null space. So if x1 belong to the null space, then a transform x1 to zero vector. And there is another vector, let us suppose x2. A times x2 also belong to the null space. That is the matrix A transform the vector x2 to the zero vector. Then the question is A times the linear combination or the sum of x1 plus x2, does this also belong to the zero vector? Because if NA is a subspace, then it should belong. So let's see. We know using property of matrix vector product that this will be expanded to this, right? And now we can simply say that this is zero vector plus this is zero vector, so this is zero vector. So we can say, and we can combine the property 2 and 3 also, right? So we can say that if x1 belong, x1 and x2 belong to the null space, if x1 and x2 belongs to null space of A, then we can say that alpha times x1 plus beta times x2 also belongs to null space. We can use both property 2 and 3. So the linear, if two vectors x1 and x2 is belonging to null space, then their linear combination is also belonging to null space. So this is the property of vector spaces, right? This is or subspace. This is property of vector subspace. So both the properties of vector subspaces are satisfied, that the linear combination also belong to the null space and zero vector also belong to the null space. So we can say that therefore null space of A is a vector subspace, right? So we have proved that null space of A is also a vector space, and we have already seen that column space is also a vector space, because there also column space contain the zero vector and also the linear combination of two vector belonging to column space also belong to column space. If two vectors belong to column space, then their linear combination also belong to the column space. Okay, so now if you see, if you have seen my previous video of column space, there I mentioned a matrix, this matrix, right? I mentioned a matrix 0, 4, 11, 0, 4, 5, and 0, 0, 6, this matrix A. And here column 1 is nothing but column 2 plus column 3. Okay, so we have seen that the column space of A is nothing but the it was what these two column, right? So it was z axis, the entire not z axis, but the sorry, it was yz plane. It was yz plane, that is 2D. So we can say that dimension, we will see what is dimension in the next video, that dimension of column space of A is nothing but 2. Okay, so now we will see the null space for this one. Okay, so we will see the null space. So this is that video, right? In this we have seen that these are the two vectors, right? This is the first one, 0, 4, 5. So sorry, this is the second column vector. The green one is the third column vector, and the purple one is the first column vector. So we see that all the three columns belong to the same plane. Why? Because the first column is nothing but a linear combination of the second column vector and third column vector. That is, the third column vector is sum of first column vector and second column vector. So the column space of the matrix A the column space of this matrix A is nothing but this YZ 2D plane. Okay, so the dimension is two-dimensional. But yeah, column space this belongs to R cube. Okay, you should never say that this belongs to R2. You should never say the column space is belonging to R2. It is belonging to R cube only, but it is two-dimensional. So the dimension of column space is 2. All right, we will see what is dimension. So using the same tool, okay, using the same tool, I calculated for this matrix. I calculated the null space. So in this case, the null space is nothing but minus 1 1 1 times t. Basically, t is any value. So this is minus 1 1 1. So what I did is I plotted this vector minus 4 4 4. I just took t. I just took t as 4 and I plotted this vector. So this is the vector. Okay. So this vector is nothing but this vector belongs to the null space. This vector belongs to the null space of the matrix A. So this matrix A, right? So this vector belongs to the null space of matrix A, and all the vectors passing through this vector, or you can say the span of this vector. The span of this vector is nothing but a line passing through this vector and passing through origin, right? So the line passing through this vector and origin is nothing but this line, minus x equal to minus y equal to minus z. So all the vectors lying on this line will be transformed to zero vector when you apply the matrix A. Okay, they will be transformed to zero vector when you apply the matrix A, because we have seen that this red vector is lying in the null space. It will be transformed to zero vector after applying A, and using this property, the second one, which we proved, that if x is lying in the null space, that is this red vector is lying in the null space, then c times x, where c could be any number, any real number, 1 2 0.3 minus 1 minus 5, anything, that is c times x is nothing but this entire blue line. Then all the vectors c times x will also be knocked down to the null vector 0. So this blue line is nothing but null space. So we can say the null space of A is a line passing through is a line passing through the vector minus 1 1 1, okay, and 0 vector. And in this case, the dimension of C null space of A is nothing but 1, because it's a line. But yeah, null space is also belonging to R cube, huh? Because see, how could it belong to R1? Because see, the vector belonging to null space is three-dimensional, minus 1 1 1, right? So if the vector belonging to null space is three-dimensional, that is belonging to R cube, then how and null space belong to R1? So never ever say that null space of A belongs to R. No, this is incorrect. Gate can ask multiple choice question on this. The dimension of null space is 1. All right, the dimension of null space is 1. Similarly, column space of A doesn't belong to R square. No, the dimension of column space belongs to 2. Okay, so we have seen in this video we have basically seen what are null spaces. All right, what is a null space, the definition, and is null space is even a subspace or not. And we have seen some good visualization of the previous matrix in which we explain the column space. Okay, so you can basically simply say that for this matrix A, okay, if I simply remove all the vectors, okay, if I simply remove all the vectors, now the input vector space is this entire R cube, right? The input vector space is entire R cube, because the column vectors are three-dimensional. So the input vector space is this entire R cube. This entire R cube is the input vector space. This gray plane is the column space, and this blue line passing through region is the null space. All right, and we have already seen this visualization. Okay, how you can see how all the vectors passing through the null space got knocked down to the origin. See, isn't it beautiful?